Okay. So today we will continue our lessons on the last chapter of PPHY 094, which is the thermodynamics. Okay, the thermodynamics. Okay, so let me share the slide. Okay, so basically this is thermodynamics. Okay, the last topic, the last chapter, which is according to your survey textbook, it will be in the chapter 12. Okay, chapter 12. But for your final, okay, it will be until chapter 14. Okay, from chapter 5 until chapter 14, right? So the laws of thermodynamics. Okay, if you look at the word thermo, that means heat. Okay, thermal comes from the word thermal. So thermodynamics meaning that we need to see some changes in the thermal part where we considering some a few processes that involve in the heat. Okay, when it involves heat. Okay, so these are the units or the subchapter in this chapter, which is first we look at the zeroth law of the thermodynamics. Okay, and then we will go towards the first law of the thermodynamics. Okay, and then we will see what is the thermal processes involved in the thermodynamics. Okay, and then lastly we will look further in terms of the second law, a little bit of the second law of the thermodynamics and its application, which involve the heat engine and also the Carnot cycle. Okay, so we will try to finish everything within these 2 hours class. All right, so first of all, let me explain, or let me um, refresh back what we have learned in past weeks about the zeroth law of the thermodynamics. Okay, so okay, if object A is in thermal equilibrium with object B, let's say that object A and object B is in thermal equilibrium, that means if you look carefully, what is this thermal equilibrium means? That means A and B should have some thermal contact. Okay, and if you bring if you bring along object C that have some thermal equilibrium with object B, we can say that A and C, okay, without any thermal contact, is also in a thermal equilibrium. So that is the zeroth law of the thermodynamics. Okay, so involve A and B in thermal equilibrium, and when B and C is also have a thermal equilibrium, so we can assume that A and C, okay, without any thermal contact, okay, will have some thermal equilibriums. Okay, so that will be the zeroth law of the thermodynamics. Okay, and then of course, when you look, when you see the applications of the zeroth law of thermodynamics, okay, we have discussed before this about how we can do some phase change, how we can transfer the heat. Okay, which I should highlight that the heat is in the unit of joule, right? Which means we transferring some energy. All right, so when you look carefully, okay, we will use that part of energy in the first law of the thermodynamics. Okay, so let's look at what is the first law of the thermodynamics. But before that, let's do some thinking about the first law of the thermodynamics. That means, yeah, you must look at the conservation of energy. Okay, if anyone is asking you about what is the first law of the thermodynamics, is about the conservation of energy. Okay, so because we cannot go further, we cannot we cannot run from the fact that the thermodynamics, we discuss a lot about thermal. Okay, thermal means heat. So heat is energy. So therefore, that is a conservation of energy. Okay, if a systems, they are saying that if a system's volume is constant, for example, you have a system volume is constant, and you give some heat to the system, and its internal energy will increase. So you can see here from the figure itself. Okay, on the left part, the very left part, you will have some internal energy U. Okay, U is the internal energy. UI means that the initial internal energy. Okay, so then you will add some heat to that particular internal energy. We are saying that everything's in the container on the first part, okay, on the container. That means it must contain with some atoms or whatsoever. So if you bring some heat to that container, so it will increase. It will increase the internal energy of the system. So these are why we're saying that the internal energy have increased. Okay, due to what? Due to when we add some heat. Okay, so we are saying that the delta U, which involve the final internal energy minus with the initial internal energy is equivalent to heat, is equivalent to the quantity of heat. So meaning that if you want to see what is the quantity of heat, okay, then we need to know what is the internal energy final and also what is the internal energy initial. And then when we do some different, we differentiate between or we do some different between final internal energy and initial internal energy, then we can have the quantity of heat. So therefore, the delta U is equivalent to Q. Q means heat, delta U is the change in internal energy. We are saying that the change in internal energy is equivalent to heat. Okay, so that's why we can say heat, right? Okay, so a system that has initial energy UI, right? After the system does the work W on the external world, its remaining internal energy is UI, the initial internal energy, minus with W, the work done. Okay, the work done on external world. So we are saying that also that the change in internal energy is equivalent to what? Equivalent to the change of UF minus UI again. That also equivalent to negative W. Also equivalent to the negative W. The work done. Okay, the work done, but that means the work done on the external world. So from this figure, you can see that, okay, if you try to bring along, okay, I'll try to look at these possible things that happens in our daily life, not in daily life. Basically, these things happens in the system. For example, we have engine. Okay, so this one happens in the engine itself. If you do have one system like some piston like this, okay, so wrapped by the some insulation material. So if you try to bring along, okay, let's say you try to bring along, you have give some W. That means you give some work to that pistons. So we can say you have increased the internal energy from, let's say, the internal energy on the initial part and the final part will be different. Okay, that means you have increased the internal energy because internal energy final is basically more compared to internal energy initial. Okay, so by doing some work, this is what happened. By doing some work, you can also change the internal energy. Okay, so now you have two. To change the internal energy is either you give heat or you must do some work done. Okay, that means if you look at first part, okay, in order to change the internal energy, you give heat or either you give work. Okay, you do the work to the internal energy and it will also change. Okay, with the facts that we have learned, that those are the things that we can do to change the internal energy. So we should combine this, okay, in order to create some law in the thermodynamics. So therefore, we have obtained delta U equivalent to Q and W. Okay, what I'm saying now is in my notes, okay, I have written down delta U equivalent to Q minus W. Okay, Q minus W. All right. So what is Q? Q is the quantity of heat, while W is the work done. Okay, but the fact that if you try to if anyone have some survey textbook, okay, they have written down the author have written down delta U equivalent to Q, okay, Q plus W. Okay, so these are uh, the the equations that you should use because this was taken from survey textbook. Okay, I want to highlight that. Okay, if anyone's okay have survey textbook, you can refer that the change in internal energy is equivalent to Q plus W. Okay, Q plus W, that means the quantity of heat and the work done. Okay, the work done. Okay, what is negative energy? If you look carefully, these are in the table 18.1 here. Okay, table 18.1 is the appendix or is the table that give sign to this kind of equation. Okay, that means delta U equals to Q minus W is correct, but according to survey textbook, delta U is Q plus W. What is the main difference between the equations in my notes and the survey textbook? Is just a matter of sign. It's plus and also negative. In this, in my notes, okay, the negative W means the work done on the system. Okay, okay, or should we go one by one? Okay, the Q positive means the systems gain heat. Okay, that means you give a lot of heat to the systems, and it's Q negative, then that means the system losses heat. Buang haba. Okay, tambah haba, buang haba. So Q doesn't matter because both have the same positive value. Okay, if you look carefully, in front of the Q is positive. Here, in survey textbook also, positive Q. Okay, the fact that the difference between these two equations is just a negative and also positive sign. All right, but don't get confused because both have the same sign. Both will solve the same problems if you learn it carefully. Okay, because we will look later in our problems or in our exercise how to deal, how to solve the problem using both equations. Okay, let's look at my slide notes first. Okay, so the Q positive will be the system's gains heat, while the Q negative means the system losses heat. Okay, while the W positive means the work done by the system, and W negative means the work done on the system. Okay, what is the difference between the work done by the system or the work done on the system? Okay, let's look at this part. Okay, if the Q positive and Q negative is the same, but in terms of work done by system means, okay, if you have done, if you are the what, let's say if you are a refrigerator or if you are a machine, you do the work in order to give something. Okay, for example, you do the work to make a machine work. Okay, the engines, okay, will start and the machine will work. So that means you do the work by the system. Okay, but the W negative means the work done on the system. For example, the work done on the system is based on okay, the environmental factor that affects you as a machine. For example, if you are in the cold position or you are in the very hot position, outside is very hot. Okay, when outside is very hot, okay, and then it will transfer some heat to, let's say, if you try to put yourself in one container and on the outside is very hot, that you can also feel the hot from the environment. That means that is work done on the system. That means on others towards you. Okay, so if the work done by system is work done doing by yourself. Okay, that is the difference. Work done by a system and work done on a system. Okay, so according to survey textbook, they will also apply this kind of work, but according to the equations, the W positive and W negative is just exchange. Exchange between this one. Okay, for survey textbook, it's just terbalik sahaja. Okay, the work done by a system is negative, the work done on the system is positive. So that is how they turn this equation becomes Q plus W. So which one should you use inside your final exam? Definitely from the survey textbook. So delta U equals to Q plus W. Need to use the survey textbook. Okay, not to use my slide note. But if anyone have using these equations, okay, make sure you have put all the signs correctly. Okay, no problem. Okay, let's look at the problems first. All right. Okay, jogging along the beach one day, you do. Okay, look at the words. You do. Okay, you do, that means you are doing the work. Okay, 4.3 10 power of 5 joule of work and give off 3.8 10 power of 5 joule of heat. Okay, you do the work. That means positive. According to my note, is positive W. Okay, positive W. Okay, what is the change in your internal energy? So we have the internal. Okay, the first question is, what is the change in internal energy? So based on my notes, delta U equals to Q minus W. Okay, Q minus W. Okay, according to my notes, okay, Q means what? Q means heat, W means work. Okay, same goes to the survey textbook is equations. Okay, Q ialah heat, W ialah work. Okay, so you do the work. So according to my notes, you do the work. That means you do the work. That means positive W. Okay, positive W. Okay, positive W. That means you need to put at that W the positive value. Okay, and then you give off heat. Give off heat. So for both situation, survey and my notes, both situation will give you negative. So at first, you need to put at negative at Q. So that means you need to put negative 3.8 times 10 to the power of 5. Then don't worry, just put negative because that is the original equation, negative. So this one first is according to my slide note. Okay, I will show you later using the survey textbook. Okay, so you do the work. You do the work. That means you have producing the work according to my notes. You do the work. So do but work done by a system. That means W must be positive. The W itself is positive. So you just put 4.3 10 power of 5 joules. Okay, so that is according to my notes. All right, so what happens if you are using the survey textbook's equations? So that means now you have delta U equals to Q plus W. Don't worry, Q plus W. Okay, so what happened is at Q, okay, again, if give off heat, then it becomes negative 3.8 10 power of 5 joules plus, yes, plus, but according to the survey textbook, if you do the work, then W will become negative. If you do the work, W become negative because it is reciprocal with the ataupun terbalik daripada slide note saya ni. Alright, so that means the W will become negative for the by system. Okay, if work done by the system, the W becomes negative. Or should I put it here like this? Okay, so for survey, okay, for survey, this one will become W, negative W. This one will become positive W. Okay, simple. If you want to refer it, okay, this one is note. Okay, I don't want everybody to get confused. So let's do it like this. Okay, this one is my notes. Okay, And this one is for survey textbook. Okay, for survey textbook, okay, the work done by the system is negative W, and the work done on the system is positive W. So if you do the work, that means you need to put negative for the survey. Negative 4.3 10 power of 5. So that means you will get to get the same value, which is negative 8.1 10 power of 5 joules. The same goes to the answer. The answer must be the same because you are applying the equations, the correct equations in the good manner. Okay, so the fact that don't worry much about this chapter, because the only things that you will get wrong is just a minus or plus. It's just the sign. Okay, will differentiate between the correct answer and the incorrect answers. Okay, so need to use that. Okay, you need to focus on the wording. It's either you do the work or you do the work, or the environment did the work. Okay, so here we can also obtain negative 8.1 10 power of 5 joules. Okay, so let's look at another questions. Switching over to walking, you give off 1.2 10 power of 5 joules of heat, and your internal energy decreases by 2.6 10 power of 5 joules. So again, I'm applying both equations. Okay, both equations must be in a good manner, right? Try to follow again and again. Maybe after we finish off this chapter, you need to watch again and again about this topic to understand the concepts of thermodynamics. It's very good. It's very useful for you to understand that, right? Okay. So the question is, how much work have you done while walking? So we need to calculate the how much work. So according to this part, okay, if you want to calculate the internal energy have decreases, the internal energy have decreases to 2.6 10 power of 5 joule. That means the internal energy is delta U. Okay, again, okay, so when you applying my slide notes, so if you want to calculate W, okay, W will equals to Q minus delta U. And then if you are referring to the survey textbook, so it will become W equals to delta U minus Q. Delta U minus Q, simple like that. Okay, so the word that Q minus W, so Q is give off, so that means you need to put negative 1.2 10 power of 5 minus with, okay, using my slide notes. Okay, the delta U is decreases. Decreases, that means you need to put there negative 2.6 10 power of 5 joules. So then you will get 1.4 times 10 to the power of 5 joule. That is according to my notes. Okay, what happens when you do from the survey textbook point of view? Okay, so what is the delta U? So the delta U is the internal energy. Decreases? Yes, decreases. So therefore, you need to put negative 2.6 10 power of 5 joules, and then you minus with, okay, you give off heat at about 1.2. Don't forget to put the negative at Q. So 1.2 10 power of 5. And then negative 2.6 plus with 1.2 10 power of 5 joule. You still will get 1.4 something somethings. Okay. But according to the problem, the equations on your left will give you negative, positive answers. Okay, W will give you positive answers, and the W on the survey textbook will give you negative value. Okay, don't worry, because that is due to the part that W negative means the work done on the systems. Okay, by the system, sorry, work done on the system. But for the survey textbook, they will get positive value, or terbalik W positive maksud the work done by the system. Okay, untuk Q minus W, and at survey you will get negative value, so that means the work done also by the system. Okay, nah, mana-mana pun memang akan mematuhi benda-benda. Okay, maksudnya kalau kita dapat satu equation tu ialah W negatif, akan bersama, W positif bersamaan dengan W negatif untuk survey. That means kalau you apply survey textbook punya equation, you will get negative value. Okay, so untuk soalan B ni, kita akan dapat dua jawapan berbeza. Okay, kalau untuk A, dia memang akan dapat sama because of kita kira internal energy. Internal energy dua-dua sama. Tetapi kalau kita when we calculated work done, okay, then you will get to see, okay, on the left side equations, you will get positive value, while on the right side, you will get negative value. Okay, so that will show you that these ones, okay, is comply to both equations. That means from my slide notes and also from the survey textbook. Okay, simple. All right. So in order to do that, we need to apply some 4 thermal processes. Okay, so that is how you did the thermodynamics. Okay, first you discuss about the zeroth law of the thermodynamics, and then the second part is you discuss about the first law of the thermodynamics. Remember, what is the first law of the thermodynamics? Delta U is equivalent to Q plus W. You need to use this part because you are using survey textbook. Q plus W. Okay. Negative W means work done by the system. Okay, work done on the system will be positive W. Alright, so without further ado, okay, I would like to introduce to you to the thermal processes. Okay, so what is the thermal processes? These are some processes that involve internal energy and also work done. Okay, so in order to the internal energy, discussing about heat and also about work done, so we need to see some thermal processes. Okay, so what is the 4 thermal processes? So from this point of view, there are 4 thermal processes. Okay, 4 thermal processes which involve constant pressure, which we also call as isobaric process, constant volume, which we also call that as isovolumetric. Okay, and then constant temperature, which involve what is called as isothermal, and lastly, all constant. So all constant, that means pressure, volume, and temperature will be all constant. So that is what we call adiabatic. There are 4 thermal processes that you should understand. Okay, so try to look carefully. The constant pressure. Pressure, if you look, the unit for pressure, sometimes we call it as Pascal. But another units for pressure is bar. Okay, how many bar? So that means it involves pressure. So that's why they get that's why they can name that constant pressure as isobaric. Okay, isobaric. So iso means constant. Okay, constant, baric means pressure, constant pressure. Okay, and if you look carefully, what is constant volume? That means isovolumetric. Okay, and then you because of the word is iso, constant, and volumetric is volume. Okay, if you look very carefully, the constant temperature, okay, that means isothermal. Okay, constant temperature, isothermal, and then everything will be constant based on adiabatic. So you can see from the pressure law, okay, PV over T is equivalent to constants. Okay, because of that, you can give that this equation becomes PV equals to from the molar mass, so nRT. Okay, so this is how they get PV equals to nRT from the pressure law. That means P and V, P, V and T. Okay, so I'll take a break for 1 minute. Okay, and then we will continue after that. All right, thank you. Okay, so let's continue. Right, on the four thermal processes. Okay, so there are four thermal processes: constant pressure, isobaric, constant volume, isovolumetric, okay, constant temperature, isothermal, and everything constant will be adiabatic process. All right. So first we look at the what is the constant pressure. Okay, in the constant pressure, okay, P will be constant and we will vary some volume. Okay, P constant, V volume. So look at the graph obtained from the constant pressure. So how can we know that that is the graph of the constant pressure? Look at the value. You still have some value uh, of uh, of pressure. So at that particular value, the graph is just a straight line. Okay, it doesn't have slopes. The slope will be zero, but okay, it will only have some one value of pressure, but you can see the volume is different. Okay, they have some volume final and volume initials. So this is the PV graph, what we call as PV. That means pressure versus volume graph. Okay, so from here we can calculate the area under the graph. So this is the area under the graph, okay, of this kind of graph. So we are saying that the work done by an expanding gas is in constant pressure is given by the area under the graph of PV. Okay, from the PV graph, we obtain the area under the graph which equivalent to work done. Okay, work done by what? By a gas. Okay, we are saying that if the system have some gas, So when we constant the pressure, so the volume will be increased. So this is what we call as constant pressure. Okay, believe it or not, okay, in the four thermal processes, okay, sometimes they will combine all three equations as all three processes together. Okay, it's not just about constant pressure. Maybe they will put also a constant volume and also constant temperature. But you need to know, okay, in here, in the constant pressure, the work done is the area under the graph. So it's given, everything about work is based on the area under the graph. Okay, so for example, these are the examples. This one is the examples. A gas expands from an initial volume of 0.4 meter cube. Okay, that is mean volume. Look at the units and the final volume 0.62 meter cube as the pressure increases linearly from 100 kilopascal to 230 kilopascal. Find the work done by the gas. So again, look at the questions they're asking about the work done by the gas. So you need to calculate the area under the graph. Regardless of, maybe you can see here the pressure is increasing, okay, but increase in the form of constant. Okay, that means it doesn't increase linearly or exponentially, right? So the pressure is increased linearly. That means it is a constant. It doesn't fluctuate. It doesn't goes up and down again and again. So we can obtain a sum of volume initial and volume final. So these are the area that you need to calculate. So based on this part, okay, in this equation, in these examples, they are calculating some trapezium. Okay, some trapezium, but this part they have calculated separately between triangle and square. So when they combine these both, they can get the value of some value equivalent to 3.4, 3.7 if I'm not mistaken. 3.7 10 power of 4. Okay, so you can do on your own, alright? But the main thing is I want to highlight that the work done is based on the area under the graph. Okay, look at the arrows. Okay, look at the arrows on the graph itself. So maybe you can also see the situation where the arrow is going that way. Okay, so don't get me wrong about this. This is just some, because the four thermal processes can be reversible. Boleh diulang, boleh di repeat kembali, boleh di kebelakangkan balik dia punya. Maksudnya kalau kita pergi ke depan, kita boleh postan balik, boleh ke belakang balik. Okay, so proses itu boleh diundur, maka berlakulah what we call that as a reversible process. Okay, so look at the constant volume. In the constant volume, the pressure also change. Okay, but in the constant value, how can we say from the PV graph? These are the PV graph. You can see here. Okay, we only obtained one value of volume. One value of volume. So from pressure initials here and here. So we can say there are the difference in pressure. So in the constant volume, you must know that because there are no work or area under the graph. There are no area under the graph for this kind of a straight line graph. So therefore, the work done will be zero. So for constant volume, the work done will be zero. So this should influence you when you are applying delta U. Delta U equals to Q plus W. So W is what? And then you can refer to that part. Okay, so you can also calculate delta U inside this kind of equation. So we can also apply the first law of thermodynamics. This is just a thermal processes to understand what will happen to this part. Okay, for example, what will happen to the work done from the pressure, constant pressure, from the constant volume. Okay, definitely work will be zero in the constant volume. So, for example, this part. Okay, A gas undergoes a three-part process shown here, connecting the states A, B, A and B. Find the total work done by the gas during the process. So again, the total work done by the gas during this process is based from A to B. So you need to calculate everything on the purple parts, which also is a area under the graph. Then again, there are three processes here. Number one, number two, don't forget about this, and number three. There are three processes involved in here, but we can only calculate the process or the work done. That means the area that obtained from the graph 1 and 3. Because 2 is 0 at that particular time. So when we calculated, we will get 18 kilojoule and 21 kilojoule for number 3. So from this start, you add everything, you will get 39 kilojoule. Okay, so just calculate the area under the graph. All right. So these are the constant temperature. Now, before this, isobaric, constant pressure, isovolumetric, constant volume, and now we have constant temperature, isothermal. Okay, so from the PV graph, okay, if you look carefully, PV over T. Okay, PV over T. So if you look carefully, pressure and volume are in the linear part, while T is on the bottom part or the denominator part. So therefore, T will constant inversely with pressure and volume. Okay, T will varies or is the direct proportional to the inverse of T. So direct proportional with inverse of T, or T will varies inversely with V and P. So therefore, we will calculate. You will see this kind of graph, which is what we call as a curve graph. Okay, a curve graph. So, for example, okay, P versus V. So at a certain temperature, so you will see a lot of different from, let's say, from 300 Kelvin to 500 Kelvin, 700 Kelvin, 900 Kelvin. They are different. They are not touching each other. But from this point of view, we can still calculate the work done, the area under the graph. Okay, so based on our knowledge in NMATS, okay, in NMATS before this, okay, you can also calculate the work under area under the graph for the curve graph. Okay, for the straight line graph is easy because it's based on the area. But for area under the graph for the curve graph, okay, basically you need to use some integration. Okay, you need to use some integration. So W is equivalent to the functional, this function against the x or the y. So now you can calculate the area under the graph. But in your level, they have simplified everything. They have simplified all the equations so that you will only see either, okay, N KT. Okay, N is number of mole. Okay, it is Stefan Boltzmann constant. T is the temperature. Ln, okay, V final over V initial, or maybe W is equivalent to nRT. That's depend on the situation. nRT, R is the some constant, T is the temperature, ln VF over VI, V initial, V final over V initial. So these are the area under the graph that you can calculate from the constant temperature, or as you call it as is isothermal process. Okay. Okay. A cylinder holds a 0.5 mole of a monoatomic ideal gas. Okay, monoatomic ideal gas at the temperature of 310 Kelvin. As the gas expands isothermally, you can look at the word used, isothermally, from an initial volume of 0.31 to a final volume of 0.45 meter cube, determine the amount of heat that must be added the amount of heat that must be added to the gas to maintain a constant temperature. Okay, how to do that, right? So here we have V initial and V finals. So look at the word used, because we are applying we are giving some heat to the monoatomic ideal gas. Okay, these are not just an expression. Monoatomic ideal gas, that means you need to calculate some things over here. Okay, so first of all, okay, we have obtained W. Okay, we need to they wants us to calculate the amount of heat. That means Q. Okay, what we know, we can get Q delta U equals to Q plus W. So we need to, what is Q? So therefore, we can have the delta U minus W equals to Q. So we need to know what is delta U and what is W. W can be calculated from the area under the graph, while delta U, you need to use some equations. What is delta U? So according to the questions, it says here monoatomic ideal gas. So based on your survey textbook, that monoatomic ideal gas is delta U equivalent to 3/2 NR final temperature minus initial temperature. But then again, these ones, okay, because of the no difference, because of the term isothermal, that means constant temperature, delta U will be zero. Okay, so again, I want to highlight that the delta U here calculated, okay, is in the isothermal part. If the question about monoatomic ideal gas in another four thermal processes, maybe you can calculate it. But in the in the isothermal, because of the constant temperature, that means temperature is the same, no change in temperature, so you cannot calculate it. Okay, you cannot calculate it, so therefore the value will be 0 for the delta U. Okay, so for the delta U will be 0 based on the isothermal. Because of what? Because of isothermal. That means constant temperature. TF minus TI both will have 0. Okay, regardless of the value. 310 Kelvin minus 310 Kelvin, so we'll get 0. So right now we just need to calculate W. So based on our terms, W is nRT ln V final minus V initial. So N is the number of mole, R is the constant value, 8.31 joule per mole Kelvin, because of the unit used in here is Kelvin. So joule per mole Kelvin, and the temperature will be 310 Kelvin. So times with ln 0.45 over 0.31. So therefore the answer will be 480 joule. Okay, 480 joule. So the value will be 0 minus with minus with minus, minus with minus. So delta U equals to Q plus W. So again, Q equivalent to delta U minus W. Okay, delta U will be 0 minus with, what is W? Okay, because of here, okay, based on our terms, it will be negative 480. So the answer is 480 joule for the quantity of heat. Okay, why is negative here? Because it's the work done by the ideal gas. The work done by the ideal gas will be negative. So same goes to this answer, 480 joule. So in adiabatic, okay, last four thermal processes is the adiabatic process. What is an adiabatic process? So again, it constant everything. The main thing here is Q equals to 0. That means no heat. No heat. The heat will be 0. So that means there is the adiabatic process. How to see the adiabatic process in the PV graph? So here, Look at, it's almost the same as the isothermal. It's almost the same as the isothermal, but it's more steeper. Okay, it's more steeper, right? So if you are the purple color here is the isothermal. So where is our adiabatic process? Here. The answer is number 1. Sorry, this one is isothermal. So adiabatic is more steeper compared to isothermal. So what is indicator of the adiabatic process is more steeper compared to isothermal in the PV graph. But another one is the heat will be zero. No heat in or out from the system. So that means Q will be 0. Can carefully, delta U equals to Q plus W, then the Q will be 0. So delta U will be equivalent to W. So what is W? You can calculate it on your own. Okay. Okay, look at how they did the questions. When a certain gas is compressed adiabatically, look at the word adiabatically, the amount of work done on it is just 640 joule. Find the change find the change in the internal energy of the gas. Find the change in the internal energy of the gas. So again, delta U equals to Q plus W. Okay, so Q will be 0. So Q will be 0 plus W. W will be based on 640 joule because the change in internal energy is 640 joule. So that's how they get the answers, 640 joule. Yeah, what I'm using is the survey textbooks equations, but according to this part, this one based on delta U equals to Q minus W. So when this part becomes 0, so 0 minus with W, but W here they consider to be negative. So the answer is 600. 0 minus with negative 640, it becomes 640 joule. Okay, so that's how they did the adiabatic process. Okay, so these are the summary of the different types of the 4 thermal processes. Again, I would like to highlight it. Okay, delta U equals to Q plus W. Q plus W. Right? So in the constant pressure, W equals to PV. Okay, don't worry much about W because every time you're discussing about W, you must calculate the area under the graph. The area under the graph. Okay, just look at another part. Okay, so the main thing is when you calculating isovolumetric. Okay, this one is isobaric process. Volumetric and okay, isothermal, and lastly the adiabatic. So adiabatic Q equals to 0. Isothermal delta U will be 0. Delta U will be 0. Okay, constant volume W will be 0. Okay, so that is the key points and where you can start it from using the equations. Okay, so right from the 4 thermal processes. Okay, now we're discussing about the second law of the thermodynamics. Okay, what is the second law of the thermodynamics? So in this part, we will discuss a lot of what is the significance when you're discussing about second law of thermodynamics. So we will take a little bit of the second law of thermodynamics to understand the concepts of hot reservoir and cold reservoir. That means hot body and cold body, different. Okay, just take a hot body and cold body to understand the laws of thermodynamics. Okay, if you think carefully, okay, the first law of the thermodynamics will use a lot of equation. Delta U equals to Q plus W. Okay, then you need to establish what is Q, what is delta U, and what is W. Okay, and then you need to apply it inside the 4 thermal processes. A lot of equations involved. a lot of situations involved. But in the second law of thermodynamics, it's just a matter of how you're going to explain about the difference in temperature in the thermal contact, during the thermal contact. Okay, when objects in different temperatures are brought into thermal contact, okay, different temperature brought into thermal contact, the spontaneous flow of heat that results is always from high temperature object to low temperature object. Again, okay, the spontaneous happens in the second law of thermodynamics is from high temperature to low temperature. That's how the thermal when there's a thermal contact, it will always be like that. Heat will flow from the high temperature to low temperature. That means these are the laws in the thermodynamics. Okay, this spontaneous heat flow will never proceed in the reverse direction. There will be no time, so you cannot see that the heat flow from the cold cold body to hot body. It must be always from the hot body to cold body, because the hot body contains a lot of energy, and energy should be transferred. Contain a lot of energy in the hot body, and then that energy will be transferred to cold body. And there will be no reverse direction, okay, in the hot body to cold body. So we can see here from the figure itself, okay, when we are boiling some water, okay, we're boiling some water, so you can have some heat from the fire itself, okay, from the flame at the below part of that. So it's either if you break into the contact, so you can see there's a conductions. Okay, conductions, that means you can feel the hotness, especially when you are holding some material that made from steel, for example. You can feel the hot. Hot from what? Hot from the flame, okay, on the bottom part of the pot. Okay, so you can feel the flame through the conductions. That means there is a contact inside the pot itself. If you are boiling the water, so you can see on the bottom part of the pot, okay, will be hotter. Will be hot first, and then that hot water will replace the cold water on top of the on the top part of the pot, and it will be exchangeable. It will exchange from time to time until it reach everybody inside the pot have already achieved some thermal equilibrium. Okay, so these are the concepts that we want to highlight, that in the second law of thermodynamics, that the heat will flow from the high temperature to low temperature. So without further ado, I would like to introduce to you to the heat engines and the Carnot cycle. So what is the heat engine and the Carnot cycle? Okay, when you talk about engine, okay, it always involve heat. Okay, because when we let's say try to heat up some everything that involve machines, that means you must involve with the engine. Okay, maybe a motorcycle, maybe a car, or maybe some electrical appliances such as iron. It must involve some engine inside that part, some engine. So if you look carefully, everything that apply, or everything that involve engine must be heat up until at one particular temperature. It must be heat up, and then they can work properly. Okay, for example, okay, we can start up the car. Okay, we can do some warm up the car. Okay, you must start the car first before you start to move with the car. So, and of course, if you let's say if you are using some refrigerator, okay, maybe you cannot see where is the heat comes. Okay, look at the back of the refrigerator. There's a part that you have maybe gunakan dia masa dulu untuk nak keringkan kasut, for example, kan, kasut basah masa hari hujan tak boleh nak jemur kat luar, so you letak dekat belakang tu, because dekat belakang tu sangat panas. Sedangkan refrigerator di dalam tu is very cold. So hot and cold meet up. And where? So we need to start with the heat in engine. So this is saying that in the heat engine, okay, we are applying or we are boiling, we give heat to some water. For example, at this part, we give heat to some water and we have increased its temperature until it becomes steam. Okay, from water, and we have learned about phase change. Okay, phase change from liquid to gas, and after it becomes steam, then it will be projected towards a steam, towards some piston. So maybe at this part they will do some work. Gerakkan kereta, sejukkan aircon, sejukkan peti ais, contoh dia. So that will be doing some work. Then after that, okay, when it have used all the work, okay, the work done, and then the steams becomes colder, and then it will reach until this part, and it will condense. Okay, it will condense and will turns to liquid, and that liquid will be pumped back to the water and then will be heat up. And these cycles will always on until you stop that things. Okay, this is how they works as a engine. Look at just a car engine. Look at everything that involve engine. So this is how they works as a one cycles. So this is what we call as Carnot cycles. That means you get something in order to do some work, in order to apply it to some applications. For example, engines, a lot of applications here. This is one of the applications. Okay, and here, so you need to get it from the energy from the hot reservoir. This is the hot reservoir. That means hot temperature things, and then you will apply. Okay, you will apply to the applications, and then it becomes. It goes back to the cold reservoir, and then from the cold reservoir, it will heat up again to becomes hot reservoir. So that cycle will be on until you stop it. Okay, the simplest things in the heat engine and the Carnot cycle. So in this particular part, when we are dealing with hot reservoir and the cold reservoir, one thing that you should understand is just how efficient is when you get that kind of amount of heat when you're applying the application. What is the left? What's left on the energy? Does you use everything from the hot reservoirs to cold reservoir? So you need to know the concepts here that we need to at least see how efficient is our engine based on what? Based on the work done, based on what's left on the engine. So you can see here, the work done is based on the heat of the hot reservoir minus with the heat from the cold reservoir. Okay, divide with the hot reservoir heat, and then you will get to see some efficiency over here. So it's either using QH minus QC over QH to get, and then times with 100%. If you want to get the efficiency in terms of one percentage, so you just multiply with 100%, or you can left it with just a point. So it's either QH minus QC over QH, or maybe you can have QH minus QC over QH times with 100% in order to get it in the percentage value. Okay, so there are one more thing that you can use, which is using a temperature. Okay, because temperature and heat is proportional. Okay, so that means if the heat is increased, that means temperature increase. So we can always use this kind of equation. Before this, we have efficiency equivalent to QH minus QC over QH, or you can write down as 1 minus QC over QH. Okay, so that is one efficiency, and another efficiency is using temperature, 1 minus TC over TH, or you can write down as temperature hot minus temperature cold over temperature hot. So that's how you get the efficiency. But if you want to get it in the percentage value, just multiply it with 100%. Okay. So that is what they call Carnot theorem. If an engine operating between two constant temperature reservoirs to have a maximum efficiency, it must be an engine in which all processes are reversible. Okay, are reversible, that means it can do again and again. Boleh diulang-ulang balik cycle dia. So that is how they get the Carnot cycle. If an engine operating between two constant temperature reservoir is to have maximum efficiency, it must be an engine in which all processes are reversible. Okay, look at how they turn it into examples. Okay, a heat engine with an efficiency at about 24% performs 1,250 joules of work. Okay, performs 1,500 of joules of work. Find A, the heat absorbed from the hot reservoir, and B, the heat given off to the cold reservoir. Okay, so how they did, right? So the efficiency of the heat. Okay, if you know heat is an energy, so energy can be transferred. It cannot be demolished, but it can be transferred to another form. Okay, so therefore, the only efficiency that we can get, of course, that we want to get the efficiency of 100%, but it's very, very impossible to get 100% efficiency. For example, if you are burning things, okay, the one of the energy, okay, cannot just you cannot just take all the energy and put it inside the engine, okay, because energy can be transferred to another form. So that's why we cannot have efficiency 100%. That will be a good indicator if you can manage to get a very high efficiency. Okay, now for example, you have 24% efficiency. Okay, 24%. That means 0.24, because 24% means 24 divided by 100, or 0.24. Okay, find the total heat again. E equals to W over QH, or E, using the efficiency. So QH equivalent to W over E. So W is 1250 divide with 0.24. You will get the heat at the hot reservoir will be 5,210 joule. Okay, so the question now is the heat given off to the cold reservoir. Again, the heat given off the cold reservoir, W equals to QH minus QC. So QC will be 3,960 joule, because that is the quantity of heat given for the cold reservoir. Or you may apply it in terms of efficiency, like we did afterwards. Okay, the I efficiency equivalent to 1 minus TC over TH, or you can use 1 minus QC over QH. So in this case, we will use 1 minus QC over QH. So the QC, you can also get the same things, 3,960 joules. Okay, so these are the main things in the second thermodynamics law. Okay, the law of the second law of the thermodynamics is considering about the conditions of the conditions of, that means the heat will flow from the high temperature body to the cold temperature body. From that, they have applied it in terms of efficiency. Okay, in terms of the efficiencies and also to the Carnot cycle. That means the cycles they get from the hot reservoir until the cold reservoir return back or recycle back to the hot reservoir. And then, of course, we will calculate the efficiency between or some heat, had some heat loss from hot to cold, or maybe from cold to hot, if it is reversible. Okay, so that is should be the end of the thermodynamics chapter. So let me do some recap on what we have learned in the thermodynamics, in which we learned about the zeroth law of the thermodynamics. Okay, so which we have discussed before this in the other chapters. And then we will learn about the first law of the thermodynamics, right? That involve internal energy, okay, change in internal energy, and also Q and W, okay. But according to the survey textbooks, according to my notes, the delta U equals to Q minus W. But according to survey textbook, delta U equals to Q plus W. So you need to use delta U plus Q plus W. The difference is here. Okay, the work done by the system is negative W. The work done on the system is positive W. How can you differentiate between work done by or the work done on? Okay, if you are a system, the work done by, that means you did the work. Okay, and the work done on is on you. That means everybody. Okay, you just stay put, and everyone around you do the work towards you. So that was mean by work done on system. Okay, right? So you can see the four thermal processes. Okay, from the constant pressure, which means isobaric, the constant volume, which means the cold are isovolumetric, constant temperature, the isothermal, and adiabatic. Okay, heat constant. Okay, Q equals to 0. Okay, so we then look at precisely what is the detail about constant pressure, constant volume, constant temperature. Okay, in constant pressure, okay, you can see the work done is area under the graph. So does with the constant volume. But in the constant volume, there are no work done on because there are no area under the graph. The graph is just in a PV graph. We use a PV graph, P versus V. I call that PV graph. So there are no area under the graph. No area, that means the W will be 0. Okay, so in the constant temperature, there will be W. But in the constant temperature, the temperature will be constant. Therefore, if you calculated the monoatomic ideal gas, the monoatomic ideal gas is 3/2 nR delta T. Okay, this delta T is the change in temperature. So if the isothermal 0, the change in temperature is not, it is the same. That means Tf minus Ti, you will get 0. So therefore, delta U will be 0. Right? So for the adiabatic, okay, the main thing about adiabatic is no heat. Okay, Q equals to 0. Q equals to 0. Right? And how to differentiate between adiabatic and isothermal? Adiabatic is more steeper compared to isothermal. So in this case, adiabatic is number 1. Okay, number 1. Right? And then we go to the second law of the thermodynamics, and we talk about, okay, a spontaneous heat flow from the high temperature to low temperature. That should conclude what is the second law of the thermodynamics. And from that, we will learn about heat engines. And we have learned about heat engines and the Carnot cycle, which are talking about the efficiency. Okay, the efficiency of the work done and the heat itself. Okay, through this equation and also these equations. Okay. Any questions so far? Do you have any questions? Ada soalan?
No, sir.
Okay. So I think that will be the end of the chapters for PHY 094. Okay. That's it. These are the last topics for PHY 094. Next week we will discuss about we will use 2 hours class. Okay, 2 hours class to discuss about tutorial our last tutorial, tutorial 12. Okay, tutorial 13, right? Tutorial 13. So please bring along your tutorial for 2 hours class lecture. Okay, so we will discuss everything inside the lecture class. Okay, so I think that's all for today. Thank you very much. Thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.